We're going to discuss the following points. First, we'll discuss the model interpretability versus the prediction accuracy. It's often an important point to discuss while building models. Then the type of feature selections and which one to be used when, and how to decide the best model out of these set of models. Subset selection, forward selection, backward selection, one of the type of feature selection. We'll talk about shrinkage methods or regularized regression models like lasso and reach model. And then how do we select the best model? By doing cross validation. We'll talk about that in brief. And then finally we'll discuss the difference between feature selection versus dimension reductions. Let's start. What is the basic statistical model? Well, a basic statistical model has a target variable y and there are set of predictors of features. So how many features you should have in the model? Often an important question in any statistical model. The trade-off is between prediction accuracy versus model interpretability. If you use a large number of variables, the prediction accuracy is likely to go up, okay, but the interpretability of the model will go down, okay. So that's the main issue or the main trade-off. If you have less number of features, it's easy to interpret, less likely to overfit, low prediction accuracy. So these are two good points, but the third one is the bad point for the pro. If you have more number of features, you should will have difficulty in interpreting, so that's a con, that's a demerit. Then it's more likely to overfit, that's again a bad thing, but we are likely to have high prediction accuracy, okay. So that's a good thing. So how do you know that what is the best set of variables or best set of features which does justice to both prediction accuracy as well as model interpretability? And that's the idea behind this session. So what are the ways to do or select the best number of features, and how to select the best model out of the given set? It depends on the choice of algorithm, the algorithm that we are choosing for to build a particular model or to solve a particular problem. The feature selection uh, or the method, feature selection method that we are using, and we'll see in the next slide what are the feature selection method available to us. Feature creation, important thing. So how many new features or new predictors that you're creating from the given set of predictors, right? So that could be many, right? For instance, if you have x is one of the predictor, you just created by squaring it, that's a new creation. You can take the log of it, so that's again a new feature. So that's nothing but feature creation. And then finally it's model selection. So your prediction accuracy or the performance of your model, both in terms of interpretation, prediction, more from a prediction point of view, it depends on the choice of algorithm, feature selection, feature creation, and model selection, right? And one of the most important thing is feature selection, and that's what is the topic for this session. Feature selection is also known as variable selection. What are the feature selection methodology available to us? This basically can be categorized into three types. The first one is filter methods. The second one is wrapper method. The third one is embedded methods. Okay, and these are groups of methods. There are several techniques within each one of these groups. Okay, so what is filter method? Okay, so filter methods have several types of selection methods, and it's also known as single factor analysis. So in econometric modeling or pure statistical modeling, people call this as single factor analysis. So what we do in this method, or in such methods rather, because there are several methods out there, it's not just we calculate or we compute the predictive power of each individual variable. So instead of combining, we just calculate or we just measure the predictive power of each individual variable. So we evaluate that. Okay, so how do you do that? Well, several ways to do it. Correlation, we find out the correlation. So we find out the correlation between target variable with respect to the predictors or the features, the x variables, right? Whether it's x1, x2, or so on, right? And we have y as target variable. So we find correlation of x1 with y, x2 with y, x3 with y, and so on. So the feature that will have the highest correlation with y is the best feature, okay? Because we want the target variable to be highly correlated with the features, right? So you just find a correlation matrix where you will have y and then you will have x1, x2, x3 and so on, and see which one of them is having highest correlation. Correlation, by the way, lies between 0, 1, 1. So the one that has the maximum, whether it's negative correlation or positive, or the modulus of correlation, whether it's positive or negative doesn't matter. The one that has highest modulus of correlation is the one to be having the highest predictive power. Okay, so here x1 has highest, x2 followed by x2 and then x3, right? So that's one way of selecting the best variable. So it comes, okay, so the one that has high information value is to be selected. Similarly, chi-square statistics is also used for categorical variable, or max, more suited for classification problem. Oh, sorry, categorical independent variable, categorical features. Okay, which has high correlation. The target variable is going to have the highest preference in the model with low correlation between predictors. So ensure that not just high correlation with the target variable, also have low correlation with independent variables. So higher the IVs, better is the variable. Okay. Okay. Wrapper method. So instead of finding out the best variable, it find out the best combination of variables. Joint evaluation of variables. Subset selection. Second one is forward selection. Third one is backward selection. And we'll see each one of them. And we'll also take an example and do it in R, just to give a demo of how this method works. So this is an inbuilt variable selection method, so we don't have to take any decision. So yes, in embedded method, the decisions are taken by the regression algorithm or the estimation algorithm. So it's very much inbuilt or automated type. Okay, so it's easier to use. So without one having to select or reject, so one need not have to select or reject a variable, right? So algorithm does that for you, known as regularizations, and what I've heard about regularizations. So it controls the value of parameters. So the not so important variables are given very low weight or sometimes zero weight, and that's why they get eliminated from the model. So the elimination process is very much inbuilt or very much automated. So you are, as a modeler, need not have to take a lot of decisions. So it's also known as shrinkage method. We'll talk about it. The famous ones are lasso and ridge regressions. So an ideal model should have good prediction and yet not very complex to interpret and use or to implement. Oftentimes in industry, you have problem of implementation or interpretation. So in subset selection, you fit models with each possible combinations of p features. Okay, let's say we have p number of independent variables or p number of features. The total number of models that you will be having is 2 to the power 3. If you have 2 features, if p equal to 2, then the total number of model will be 4. So the idea is to use every combination, right? So you will have with only x2 and with both x1 and x2. So this one is the first model with only x1 as the predictor, and second model you have only x2 as the predictor, and third one you have x1 and x2 as the predictors. So that 3 model. We ideally should have 4 model. Well, the fourth model is nothing but only intercept. Okay, so it's just a mean intercept. P is, let's say, 3, then total of models is going to be 2 to the power 3 is equal to 8. If P is 4, then it's going to be 16. If P is 5, it's going to have 32. But if P is 10, you're going to have a very huge number of model, and that's very difficult, right? So it requires a massive computational power, and not always you have availability of massive computational power. So to reduce the computational power, the algorithm is broken into 2 stages. So what it does is, in first stage, first all combination of models that has only k predictors out of total p predictors, so and pick the best model from the set of k predictors. So what happens is that models and so on, right? From each number of predictors, you will have one best model, right? With one predictor, you will have one best model out of p models. Okay, so the way to select the best model out of the set of models is to use test error, not to use training error. Okay, because you are building the model in training data. So if you use training data to use to select the best model, that's going to be very biased. So use test error. Test RSS for regression problems and test deviance for classification problems. So, depending on what type of problem you're dealing with. What's the problem with subset selection? As we have already discussed, problematic when you have high dimension or when the number of features is greater than 20. It is like very difficult to do the computation. It's almost impossible, right? So best subset selection is impossible when p is greater than 20, and that's where you're going to use what is known as stepwise selection. And there are three types of stepwise selection. One is forward stepwise approach, backward stepwise approach, and then third one is hybrid approach. So the forward stepwise approach is like this. We start with a null model and then you keep on adding predictors or features to the model one at a time. This is important to remember, and choose the best model among the best of k based on RSS. Okay, now you remember how you took k, right? When k equal to k equal to 1, you have p number of models, right? Because with x1 you can have one model, with x2 you can have one model, to xp you can have another. So you have p number of models in such way. So one of these models will be the best, right? When k equal to 2, then you take two variables at a time, x1, x2, then x1, x3, and so on, and then we'll have one model from that, right? So we have shown that here in this table. Let's say x1 is the one that gives you the best model. Okay, now what happens is, if that gives the best model, then that is retained in the model. It's never gets dropped. Okay, so in forward stepwise, you retain that model and it's highlighted in in bold. Okay, when it's a two variable model, subset selection gives you x1 and x3. Okay, in forward we just added x2 and saw whether that is actually working fine or not, because for a two variable model x1 x2 does a good job. So we just added x2, and once that retains in the model, that never gets dropped. So in the third model we have x1 x2, but x3 was not part of it, which directly went ahead with x4. And the fourth model with four number of variables, you can see x1 x2 x4 and x5. Okay, so there is no x3, so x3 got dropped here and you do not have x3. So x3 did not meet what is known as an entry criteria. If it is there in one variable selection, it will definitely be there in two variable selection, right? Now if you look at subset selection here, x4 is there part of three variable model, but it's not part of four variable model. So that will never happen. It's not part of variable. You can see there's no x4 here, but here with three variable it's there, but that will never happen in forward stepwise. In forward stepwise, you can see if it's their part of the three variable model, all three variable x1, x2 and x4 are a part of four variable model. So this is one type of selection method, variable selection method, which is reverse of forward. You start with all predictors and then you drop one at a time. So in forward we start with one, then you go to two variable model, three variable model, and so on. And it's just the opposite. You start with p number of variables and then p minus 1, p minus 2, and so on. So here is a comparison. We have backward stepwise, we have forward stepwise. So you start with all the predictors available. Let's say you have 5 predictors, x1, x2, x3, x4, x5. Now here in the first step we found out that x2 is a bad variable or not so important or the least important variable. It gets dropped here. So we have x1, x3, x4 and x5. If a variable is dropped, it never gets added again. Okay, so in the four variable model you find that x2 will never be there. X4 has been dropped in the second, x3 has been, so you cannot have four models or five models. You can only have x1, because x1 is the one that is never dropped in the previous times, right? In the last 3 or 4 steps x1 hasn't been dropped, so in the final model you can only have one choice or one model in that case. On the other hand, forward you just do the exact opposite. So computational power requirement is similar to that of forward. Okay, and the selection method is through RSS and deviance that we have discussed, that you have more choices now. So you build a model with backward approach, you build a model with forward approach, and then you take the final model from backward and take the final model from forward, and then compare their do the cross validation with test data and see which one is doing it, giving you the best prediction. And this types. Forward you have variable which is included never drops out, right, in the next step. In backward, a variable already dropped from the model never shows up. So it combines, the hybrid model combines both. Okay. So hybrid starts with adding one variable at a time like forward, but drop variables during the process. Gets dropped, it never shows up again. So it combines the features of both or the qualities of both this type, forward and backward. So it's more like subset selection. So it takes more combinations, right? Selection, which takes both forward and backward approach, but it has the it has the computational advantage. That means it's not as computationally intensive as that of subset selections. So instead of using subset selection, you can instead use hybrid, which does more or less like subset selection but with less computational requirement. It's very simple. Syntax is very simple, right? You can see the function is reg subsets and salary is the target, and here we are going to use all 19 variables. Probably we have used 8, I'm sure. I'm not sure whether it's okay. If I want to use all variables, you have to give a maximum, otherwise it's going to keep it down actually. Okay, because if you have large data set, the computational power is going to be massive. Given that it's a small data set, we can actually use 19 variables, which is okay. But if it's a large data set, it's going to be, so that's why it restricts to only 8 variables. I'm not sure whether I've used 19 or 8, but let's see. So it was 8 actually. Okay, I can extend it to 19, not a big deal. Okay, so you can see when k equal to 1, so one variable model, you will have 8 different models, right, with each one of these variables in place. This gives the best model. So from the first, when k equal to 1, you have the best model with CRBI. So your salary is best predicted as a function of CRBI. So that's one of the predictors or features. Okay, when you have two variables models, you have many number of models, right? When k equal to 2, so you can see star over here, hits, and then CRBI. So when you have two variable model, the best prediction is given by the function of CRBI and then hits. Okay, when you have three variable model, you have hits and then you have CRBI and then you have putouts. What is the best one? Okay, how do you do that? Simply do the R square, just plot the R square or the adjusted R square. Okay, and we'll do that for test data, not for training data. Okay, so when you do that, you get R squares values. So here we have taken training data, not test data. If you have test data in place, you better do it on test data. But even if you don't have a presence of test data, you have smaller data set and you can't divide into training and test data, still you can use. When you do a summary statistic, you can see the R square value is actually going up with more number of variables. So that actually is failing us. This actually is disappointing us by saying that we are using subset selection for bringing down the number of features. Because if that's the case, the prediction power is going up with adding more number of variables. So adding more number of variables is actually good. That's ideally is the thought process. However, this can be validated by plotting the BIC value, and that's where we have done. So we have plotted the BIC value. So wherever you see the BIC, this dark spot actually touching, you see this is one case, this is one, second, third, fourth, 5, 6 or 7. Okay, I think 6 or 7. So either 6 variables or 7 variables is actually giving you the best model with a good interpretation. So BIC actually penalize you for having more number of variables. Okay, so with this plot you can actually find out what is the best model. Remember, this is all required when you are using training data for validation, which is actually not the ideal thing to do. But you already have a test data, you need not do this. What you need to do is that just calculate the the root mean square error, the RMSE, for the test data set for each model. So for now we'll compare forward and backward. So we just started with subset selection. We'll do forward and backward. Syntax is same except the fact that when you do not use any method, by default it takes subset selection. When you use methods forward, it is going to do forward selection. When it's going to use method, syntax is wrong slightly, is method ME, backward, then it's going to give you backward regression results. and that's what we are going to see. So here you can see that if something is added, like this is the forward one, if something is added, it never gets dropped. Now you will see CRBI has been added in the first model. When k equal to 1, you have CRBI in the model. Now you can see CRBI is there in all models. Now you can see it's star in all models, right? And that's the beauty of forward selection. It constrained that in all selection, all types of model, this has to be there. In the second model, you can see hits get added, right? And you can see in the subsequent models, in all subsequent models, you have hits as one of the independent variable, one of the features. Similarly, the third model, you can see what is there in third model. Okay, we'll see here. So in third model, put out is there. So you can see in all subsequent models, put out will be there. Okay, so that's the main idea behind forward selection. Okay, so again, if you are using training data set, just look at the BIC plot and see in how many cases it's giving you the best prediction, and then choose the one. Otherwise, you'll have monotonic relationship. That means your ask query will simply be improving over number of with increasing number of features. So BIC plot is going to tell you what is the best set. Okay, now that we have seen the different types of these selection methods, let's go to the last one, which is the embedded method. Okay, also known as shrinkage method. We also call this a regularization regression models, and I'm going to give you what regularization is. One video I have made on regularization. If you want to learn more about regularization, it's there in this video in the description section. So it's a technique that regularizes the estimates, or it shrinks the coefficients to 0. So you have beta coefficients, right? These beta coefficients will be very close to 0 or either equal to 0 sometimes. And that actually, whenever it's equal to 0, then that variable is as good as not present in the model, or that variable is considered to be not part of the model. That's one type of selection method, right? Or rejection method rather. So how do we do shrinkage or regularization? So there is a slight change to the estimation process. So in the estimation, in the linear regression estimation, or any regression estimation, when you're using least square estimation, you are basically minimizing the root, the RSS, right? The residual sum of squares. And how to compute the residual sum of square? Is the summation of sum of 1 equal to 1 to n, yi, which is target, minus beta naught minus summation of j equal to 1 to p, where p is the number of predictors, beta I xij. So this is the set of features or set of predictors. These are estimates. Beta naught and beta I are the estimates, right? And this is how you compute your RSS, root mean square error. In embedded method, you just add another term. So this is the term that we are adding to the RSS. So RSS is computed like this in normal least square estimation. In shrinkage method, to the RSS we add another term and then minimize, and then we minimize the whole thing. Okay. Now what is the idea behind this? Well, the idea is that to ensure that the beta values get low value. So beta should get low value. And what is the benefit of it? Because what happens is that some unimportant variables which are having very high impact on your target variable should get low value, so that it gives a better prediction. Okay. And there are basically two types of shrinkage method, lasso and ridge. So lasso is the one, so this is ridge method. This is called the one that we have seen ridge. In lasso, we just do a slight change. We just add RSS, and to that we add this term. So instead of squaring the beta, summation of beta, we have taken the summation of square of beta values. So here we have taken the modulus of that, modulus of betas. Okay. Now we are minimizing this, minimizing RSS plus lambda and the summation of modulus of betas. So this is the difference. Here it's modulus, and there it is square of the parameters or the coefficients. There's fundamental difference between that. Okay. And what is lambda? It's called tuning parameters, and we'll talk about it later. Okay. So in lasso, so the earlier one was ridge, where your betas will tend to be 0, but will not exactly be 0. Whereas in lasso, here some of the coefficients, some of the betas will be 0, exactly 0. So when the coefficient is 0, that variables with which this coefficient is associated is actually getting dropped from the model, and that's the selection method, right? That's how we reject some of the variables. So we reject variables which have beta is equal to 0, and it's automatic. You don't have to do it. Like in the previous case, in subset selection, we had to run it, we had to check the BIC plot, we had to check the R square, do the cross validation and so on. Here we don't have to do anything. So in the estimation procedure itself, we found some of the beta values to be 0 by changing the estimation function or the cost function. So this cost function now is changed, and it automatically takes care of the variable reduction. Okay, so given that beta values becomes 0, lasso is considered to be a variable selection, not Rees, although Rees also is sometimes considered to be very helpful, but from a variable selection point of view, lasso is actually very useful. Now some people confuse that dimension reduction is also very similar to feature selection. Dimension reduction is actually different. In dimension reduction, you do not drop any variable, okay, or you do not select the variable out of the set of variables. You actually combine. Let's say you have let's say you have 4 variables, x1, x2, x3 and x4. So principal component analysis is one of the dimension reduction variable. There could be other dimension reduction with methods like your factor analysis and so on. So you can combine these 4 features in such a way that it reduces to a smaller set of features. Okay, so here by combining x1, x2, x3, x4, we could find 2 different variables called g1 and g2. Of x1, x2, x3, x4 combiningly is retained by g1 and g2, but they are 2 different variables. So this is a linear combination of some of these variables, and g2 is also a linear combination of some of these variables. So we are combining variables to find principal components. Okay, but we are not dropping x1 and then going ahead with x2, x3, x3. So that's not happening. That's what happens in feature selection. Whereas in dimension reduction, you combine variables to come up with composite variables or 2 completely different variables. So these are g1 and g2 are composite variables which are some sort of a linear combination of x1, x2, x3 and x4, and then these variables retain the prediction ability of the initial variables. But the bad thing is that you can no more interpret the original variable, because that's now combined together with some sort of a linear combination. But from a predictive model point of view, it actually does a good job, because it reduces the number of features finally, but not through feature selection, but through dimension reduction, because we are bringing down by combining features here.